we started a couple of weeks ago trying to see what we can do when it comes to pre-processing of our data. And the good news is that the iterative process of machine learning modeling makes it very easier for us to manipulate and get our work better every time we try to improve upon it. So we said that there is no really need to spend so much time on pre-processing. You go for pre-processing that is very important, like missing value, because so you go then, because you always have the opportunity to come back. See, there's this iterative process that should always guide our way. So because of this iterative process, we can go to modeling, then performance measure. If it's not okay, you are yet to be satisfied with your output, go back to the modeling. You can do hyperparameter optimization. You may even change the algorithm altogether just to improve your result, because the essence is we want to improve our performance as we have more changes in our data set. So sometimes if optimization, changing the algorithm may not be the solution to the weakness of your model, you may have to go back to the previous stage of data preparation all afresh, or feature engineering, trying to break down feature, a particular feature into multiple, like dates, could be broken down into year, month, and date. So you can get 3 features from one feature. These are some of the stuff we do in feature engineering. And then you start the process again, go forward. So there's this iterative process. You always have that freedom to do and then check out and towards getting your result even better. So last time we started by looking at what is outlier, what is the impact of outlier on data set, and how to detect outlier. This is where we get to what we are going to be discussing today, how to detect outlier. We've introduced ourselves to the definition of outlier, and we compare to looking for outlier. It's like a mining needle in a haystack. Mining a needle in a haystack. So very challenging. You have very little time to do it. The needle is very small, so not very conspicuous. So you have to do it as fast as possible. And we say one of the reasons why outlier compared to missing value is more challenging to find. So looking outlier main issue with us. Once we are able to detect outlier, removing it, you use the same method we have described in our previous section. You can check out the video, how to treat missing value. The same methods you can use to treat missing value can also be used for treating outlier. However, the major problem of outlier is how do we detect outlier? Because what is an outlier in one feature may not be outlier in another feature. So you cannot just say, okay, anything above 1,000 value is the outlier. No, 1,000 under salary could be normal. 1,000 under age of student is abnormal. You can't have a student that is 1,000 years old. This is why outlier is very challenging, because what is outlier in one feature may not be outlier in another feature. So we describe this, and then we give example of outlier. You have all the data that could run a particular medium. However, the outlier is going to stand out, separated from the other data. Then you know that, okay, this is possibly an outlier. So we've described the impact of outlier. We refer us to our earlier video, which has been posted in our YouTube channel, to see what are the impact of outliers and how do we deal with it. We demonstrated that by looking at this simple example, whereby this is data. You find the mean, the median, the mode, the standard deviation. Once you include just one outlier, you can see that it changed the mean totally. From 5.45, it became 80. Median mode remains. However, you can see the impact on the mean and the standard deviation. And mean and standard deviation will go a long way to actually determine the distribution of data, which we have fed the modeling outcome of whatever model you are deciding to give. That is why the effect could be very, very serious. Once the mean is affected and the standard deviation is affected, definitely the entire distribution of the data set will change. And then we describe also why it is always difficult to detect outliers, because anomalies differ. What is an outlier in one feature might not be an outlier in the other. And we finally compare detecting outlier to finding a needle in a haystack, as we shown in the earlier photo, which really show that how challenging detecting outlier may be. So because of this was where we stopped last time. We are going to start discussing how do we detect outlier, since we said it's very challenging to detect. Remember, missing value is not difficult to detect. You can easily see it. But the problem was, how do we resolve it? How do we treat missing value? We describe them extensively. So the same thing goes for outlier now. Detecting it is a big issue. So in missing value, there's no need to talk of method to detect missing value. It's very straightforward to detect missing value. However, to detect outlier is the big issue. Once you're able to detect outlier, resolving it, you just go back to all the methods we described in missing value treatment. We can easily use them for the outlier. Now, we're going to discuss detecting outlier from three types of methods. Graphical method, which is very common, straightforward. Statistical-based method, and distance-based or model-based method. Now, let's look at the graphical. Let's look at the graphical-based method. See, graphical-based method is very common. You can use even the basic, as common as using Excel, can do that for you. So it is the most commonly used method for detecting outlier because it is visualization-based. Visualization is the most, which is the same as graphical, most commonly used method for detecting outlier. So just put your data set into the system. You can see here, it is just quarterly, this is quarterly modeling of quarterly income. It's 2007, January, and the lies. You want to just put it into a plot. You want to see, okay, is there any outlier in this data? Then you can see it. All the data set, majority of the data falls between this place and this place. Anything outside this zone and this zone, we refer to them as outlier. And you can see these two, they can be referred to as the outlier. Easily you can visualize it. When you produce your box plots, a simple Excel can be used, a lot of packages that can be used to do this. Then you can see that those that are outlier will quickly separate themselves out. The data is very few, so you can easily visualize it yourself here. However, imagine you are dealing with millions of samples. So you see the power of box plot. Box plot will separate all those ones that are outliers. And then you can also use histogram. Like this, you can use histogram to also detect it. By histogram, you'll be able to see those that are above their peers in an abnormal fashion. We can also use scatter plot. All these are visualization methods, or we call it graphical approach. So by plotting scatter plot of your data, you see the whole data set, majority are A. You can see these two, they are created from their members, from their peers, with very big margin. You can easily spot that, oh, these are the outlier. That is detecting outlier using graphical method. Because if outlier is in your data, then you may not be able to achieve the result you are supposed or you might have achieved. Then the statistical-based approach. In the statistical-based approach, here you try to find or calculate or display the statistical characteristics or attributes of your data set. We want to look at the data distribution, the parameter of the distribution, like the mean, variance, and sometimes we go to confidence limit. By looking at the statistical values of your data or attributes of your data, experienced people were able to say, oh, this data is likely going to have outlier. But we still need to go back to the graphical method to really detect where is that outlier. But by looking at your statistical distribution or characteristics of your data, we can tell that there's problem of outlier in your data. This statistical method has a limitation in the sense that most of the tests are for a single attribute. If you calculate the mean, you can only calculate mean for one attribute at a time, mean for another attribute separately. But in many cases, the data distribution also may not be known. For high dimension, especially if for high dimensional data, it may be difficult to estimate the true distribution of your data. However, it's still an option to be used. For example, whenever we have data set for analysis, we ask the student to first of all provide basic statistical attribute of the data set. Like this is age attribute. You find the mean, the median, the standard deviation, the maximum, and the minimum. So when you look at the maximum and the minimum, some people calculate the range. Range being the difference between the smallest and the maximum, the largest value. So we can take that by getting the difference between these. If the range is really huge, then that will give you some idea about how your data is. You also look at the standard deviation. Deviation here is very small. Look at this deviation. Look at the deviation here. So we look at as expert, people look into this statistical analysis and be able to give an idea about, oh, I think you need to check out for your outlier. There's definitely like outlier may be in your data. And already remember I told you that the fact that there is a huge difference in the range, a particular attribute may not actually mean that there's the outlier. Because what is outlier in one feature may not be outlier in the other feature. And that is why the graphical method stands out as the most common. And for now, we can say the best way to detect outlier in your data set. As we have demonstrated earlier, the statistical method has several limitations that may make you not to be able to tell directly if this is outlier or not. The third method of detecting the outlier is the distance-based approach, where we can use like the k nearest neighbor. There are three major approaches in this respect after representing the data in a vector as a vector of features, of course. So we have the nearest neighbor based. Look at the nearest neighbor and see how close is it. We have the density based and we have clustering. Among the distance-based approach, clustering is very, very efficacious. For example, this is an example of a set of cluster created. Imagine you have a data set that looks like this. So I try to cluster them into like 1, 2, 3, 4, 5 clusters. Then we can see that there are several data that are forming into these, another one forming into these. Why this one is a little bit separated, standing alone. This also is standing alone. This one is also trying to form another cluster with 5 members. But we can tell that these are more of outliers than natural clusters. See, sometimes we use this clustering as a pre-processing for our predictive solutions. Sometimes the data has so many noises, outliers. Okay, we try to use the cluster. First of all, cluster the data. These 2 categories, they are the main category. Let's say somebody say, okay, this data contains data for people who are suffering from kidney disease and those who are not suffering from kidney disease. But we don't trust the data. So we want to see if there are outliers, if there are some noisy data, then we put it into clustering. So after clustering it, you see majority class 1 will be here, majority class 2 will be here. You see, we know this is class 1, these are people who are suffering, these are people who are not suffering. Then this one will be removed from the data because they are not closely related to other data, and they are going to pull your modeling power down. So we try to remove them. That is when we use supervised and unsupervised learning combined together in an hybrid setting, using the unsupervised learning to remove the outliers while leaving the data with, hopefully, better samples that can ensure that our model output is good. So this is an example of clustering. So we use it to detect that if there is an outlier in your data or not. And it's very, very popular that I can just mention. You can easily use it to detect all the characteristics of your data. So we use it to show that, okay, there's outlier, and then we can figure out why is that outlier, and we can remove them. Because outlier will create a bigger distortion in the performance of your model. Then the nearest neighbor also. So, okay, nearest neighbor, and it's like building another model to be able to identify, okay, if this is an outlier or not. You try to see and make use of it to detect why are you so far away from your neighbor, then something may be wrong with that data sample. Now, having discussed the 3 methods of detecting outlier, we can see during missing value, we stress how to treat missing value. But here, we are discussing how to detect it. So after detecting outlier, like I said, very challenging, then we move to how do we remove it. This point, we're not going to spend much time on this, so we refer to the video we made earlier that discussed how to treat missing value. All the methods of treating missing value are also applicable to treating outlier. The first method is, and the best method is to go back to the original source of your data. Go to the original source of the data and get the correct data to replace the outlier you have detected. This is the best way to do. It is when this option is not possible, we know that in reality, it's really possible to go back to the source. You may not even know the source of the data. People who produce the data may have retired from service. We cannot locate them. They are on leave. So many reasons why we may not be able to get it. But have it at the back of your mind. The best way to treat outlier or missing value is to go back to the original source of the data and let them replace with the correct value. Because when you are treating missing value or outlier, we're actually introducing fake data. That is why treating is the last option we go for, or replacing imputation method. See, so the first method is to go back to the source to get the original one so that you know you are modeling with correct value. However, due to the limitation and the reality, we may not actually have that option. So we go to the next option, which is deleting features or observations. At that point, you go to your features, you go to your table, and then see your table, which feature has so many missing value. Then, if there are so many missing value, we give us a ratio last time when we discussed the missing value. Calculate the ratio. If a particular feature has more than the minimum you are expecting, then you can delete that, remove it totally. It has so many missing value. However, if your features are so few, you have only 3 features. How do you want to remove those features? In that case, you may have to start removing the samples. This is sample 1, sample 2, sample 3, sample 4. Those samples that have so many missing value within them, you can remove them. That's another way to delete it. To treat outlier. We remove those with missing value. The samples that have so many missing value in front of them, you remove them. But sometimes you have fewer features. You also have fewer samples. Removing anyone is not an option for you. In that case, we go for imputation method. Imputation method. We try to impute, that is, try to replace the outlier with the imputation method, which is, it could be mean. We can use mean. You calculate the mean of that feature. and then use it to replace all the outlier under that feature. Calculate the mean for the second feature. Use the mean to replace all outliers in that particular feature. And then it continues like that. We've described all the imputation methods, mean, median, mode. And sometimes you can use even machine learning models to predict the value you are supposed to use to replace it, like k-nearest neighbor. All these methods that we described for inputting missing value, they are also valid to be used for inputting outlier. And we may also transform the data using the binning system or method by trying to say, okay, we have outlier 10, 1,000, 200, 300. We try to create binning for them by saying, okay, between 10 and 500. We can call them C. Between 500 and 1,000. We can call them D. That we try to transform the data to ignore the effect of the outlier. We don't want 1,000 in age and the likes, and we don't want to use all these treatment value that are inputting, and because inputting value, you are not sure the mean you are actually using is close to the original value. So that's why we inputting a value for replacement is the last option we do, because it's always better to have the original data as much as possible. So we can use the binning method to transform our data and ignore or remove outlier by using the idea of transforming and binning value transformation. So it is also a form of variable transformation that we do resort to when we have to treat outlier. So in addition, with this transformation method, in addition to all the methods we have described under the missing value treatment, they are all valid to be used for treatment of outlier. So by so doing, hopefully you'll be working with data that is better than. Which method is better? I know people want to ask. There's no method that is better. This is what we call the principle of let the data speak. Let the data speak. Data speak. And that's why data science and machine learning projects are usually group-based. Some group member will be investigating the effect using mean imputation. Another group member should use median. Another one you use mode. Another one you should use k-nearest neighbor. And then you can compare your result. After you have used this method, then try to do modeling and prediction or whatever solution you are developing and compare the result. Whichever one gives you the best result, maybe mean imputation gave you the best result, you go with it. It doesn't mean that next data you are going to model next 2 weeks, that you are going to use mean and it's going to give you the same best like before. No. This is let the data speak. The insight inside the data set are coming in a special way, in a different way, compared to the one you have modeled earlier. So if you stick to your gun, oh, I used mean last year, it worked for me, I'm going to use mean. You are wrong. Mean may not work for the new data on your table. So you have to always check which of the methods that will work for me. Oh, in the literature, we notice that mean always work. That is just we notice. Doesn't mean the present data will follow that pattern. And that's why we always have to work with the principle of let the data speak, which means we have to try different methods, even algorithm that we are going to use in building your model. You always have to keep coming back and checking. For example, when you want to do the modeling, which algorithm to use, I use k-nearest neighbor because it's very simple. I use decision tree because I can easily explain my outcome to my client, but that doesn't guarantee that, okay, they are going to be always getting better results. It is always good to check out different algorithms, check out different methods of pre-processing before you can conclude that, oh, my algorithm is not good. My performance, my model is not good. I didn't get good model. Some people will just start the data set, they normalize the data immediately. Normalization is good, but it breaks the principle of let the data speak. Sometimes your data may perform better as it is originally from the client. However, because some people have so much obsessed with normalization. The moment they get the data, they normalize it. And then they start the modeling process, and they may miss the insight in the data. So, and we have seen practical example of this. Where did they normalize? They struggled to get better results. They couldn't, brought it to me, and I asked, where is the original data? This data looks normalized. They said, we have the original data, but normalization always produces good results. I said, no. Can you bring back the original data and do the modeling? Surprisingly, they got better results with the original data before the normalization. And I said, this is the principle of let the data speak that I've been talking about. So always check the original data before you start rigorous pre-processing. You only do pre-processing that is very compulsory, like missing value treatment. Even in few cases, if I'm using decision tree, I may not even need to do missing value treatment because decision tree and its family can still work without even treating the missing value. They have an inbuilt mechanism to deal with missing value. However, other algorithms may not support that, like support vector machines and others. They want the missing value to be treated. Then we can say that apart from missing value, no other pre-processing method is compulsory. So run the experiment on the original data, move forward, try several algorithms, check your performance measure. If it's not better, keep going back. Then you may have to go back after you have exhausted all the options in the front end. We have done hyperparameter optimization. We have changed several algorithms. We have even built ensemble, yet we are not getting what we expected or what is expected of us. Then we may go back to feature engineering. We may go back to pre-processing, normalization, outlier detection and treatment, and also further methods. And that's why it's always good to work, especially at the beginning, with experts to guide you through the process. So these are the iterative process of machine learning to take notes, while also noting some of the pre-processing method we have described, the missing value treatment, how to locate them, how to treat them, the best method to be used, and also outlier treatment. How do we detect outlier? Detection is the most challenging part of outlier. Once you're able to detect it, just bring all the methods for treating missing value. They can also work for the outlier detection. So because of our time, I believe this is what we're going to have for the day. We're going to give room for question and answer if applicable. Thank you very much for listening, and we wish you all the best.